Look up on a clear day, and you might see two aircraft crossing the sky at similar altitudes. One leaves a long white trail stretching to the horizon. The other leaves nothing at all. It looks like it's not even there. Both are commercial jets. Both are burning jet fuel. Both have engines producing exhaust. So why does one create a visible trail while the other flies invisibly? The answer involves thermodynamics, humidity, and the invisible properties of the atmosphere at 35,000 feet. And once you understand it, you'll be able to predict which aircraft will leave trails before they even pass overhead. These trails are called contrails, short for condensation trails. And despite what some people claim on the internet, they're nothing more than artificial clouds. To understand contrails, you need to understand what jet engines actually produce. A jet engine burns kerosene-based fuel, combining it with oxygen from the atmosphere. The combustion produces several things: carbon dioxide, various gases, particulate matter, and most importantly for our purposes, water vapor. For every kilogram of jet fuel burned, roughly 1.2 kilograms of water vapor is produced. A large jet engine can burn several thousand kilograms of fuel per hour. That's an enormous amount of water being released into the atmosphere. At ground level, this water vapor simply disperses into the air. You don't see it. The atmosphere at sea level is warm enough and has enough capacity to absorb additional moisture without any visible effect. But at cruise altitude, conditions are radically different. At 35,000 feet, the temperature is typically minus 50 to minus 60 degrees Celsius. The air pressure is about 1/4 of sea level pressure. And most importantly, the air's capacity to hold water vapor is extremely limited. When hot, moist exhaust from the engine meets this extremely cold air, the water vapor doesn't just stay as vapor. It condenses almost instantly into tiny water droplets. And at these temperatures, those droplets immediately freeze into ice crystals. Billions of tiny ice crystals form in the exhaust plume. They scatter sunlight, appearing white. This is the contrail, a linear cloud created by aircraft exhaust. The physics is identical to what happens when you breathe out on a cold winter day. Your breath contains water vapor from your lungs. When it hits cold air, the vapor condenses into visible mist. The contrail is essentially the aircraft breathing out in the cold upper atmosphere. But here's where it gets interesting. Not all aircraft at high altitude produce contrails. Why? The formation of contrails depends on the relationship between engine exhaust properties and atmospheric conditions. Specifically, it depends on temperature and humidity at cruise altitude. If the atmosphere is warm enough, the exhaust cools but doesn't reach the point where condensation occurs. No contrail forms. The water vapor remains invisible. If the atmosphere is cold but extremely dry, condensation might occur briefly, but the ice crystals sublimate back into vapor almost immediately. Any trail that forms disappears within seconds. For a persistent contrail to form, the atmosphere must be both cold enough for condensation and humid enough to sustain the ice crystals once they form. The ice crystals need ambient moisture to survive. In dry air, they evaporate. In moist air, they persist. This is why you see some aircraft leaving trails and others not, even at the same apparent altitude. They might be flying through different air masses with different temperature and humidity characteristics. A difference of a few hundred meters in altitude can mean completely different atmospheric conditions. There's a scientific tool for predicting contrail formation called the Appleman chart, developed in the 1950s. It plots temperature against humidity and shows the conditions under which contrails will form. Meteorologists and atmospheric scientists use it to predict contrail-favorable conditions. The trails themselves come in several varieties. Short-lived contrails appear and disappear within seconds to minutes. These form when the atmosphere is cold enough for initial condensation, but dry enough that the ice crystals quickly sublimate. You see a short white line directly behind the aircraft that fades as you watch. Persistent contrails remain visible for minutes to hours. These form in cold, humid conditions where ice crystals can survive and even grow by absorbing additional atmospheric moisture. They can spread and eventually become indistinguishable from natural cirrus clouds. Persistent spreading contrails are a particular category. In highly humid conditions at cold temperatures, contrails can expand dramatically, covering large areas of sky. Multiple aircraft trails can merge into extensive cloud sheets. This spreading phenomenon has actually caught the attention of climate scientists. Contrails and the cirrus clouds they create have a measurable effect on Earth's climate. They trap outgoing infrared radiation, creating a warming effect, while also reflecting incoming sunlight, creating a cooling effect. The net impact is complex and still being researched. Some estimates suggest contrail-induced cloudiness may contribute to aviation's climate impact almost as much as the CO2 emissions themselves. This has led to research into contrail avoidance strategies, where aircraft might alter altitude slightly to avoid contrail-favorable conditions. Now, let's address why two aircraft at seemingly the same altitude produce different results. First, they might not actually be at the same altitude. Aircraft at 35,000 and 37,000 feet look identical from the ground, but those 2,000 feet of altitude difference could mean completely different atmospheric conditions. One might be in cold, humid air, the other in slightly warmer or drier air. Second, even aircraft at exactly the same altitude might be passing through different air masses. The atmosphere isn't uniform. Pockets of different temperature and humidity exist at the same altitude. An aircraft a few kilometers behind another might encounter different conditions. Third, engine efficiency matters. Different engines produce exhaust with different temperatures and water content. A more efficient engine produces less waste heat and might have different contrail formation characteristics. Newer, more efficient aircraft might produce different contrail behavior than older models. Fourth, there are diurnal and seasonal variations. Atmospheric conditions at cruise altitudes change throughout the day and year. Morning flights might encounter different humidity than afternoon flights. Winter conditions differ from summer. The variability is why contrails appear inconsistent. It's not that some aircraft are spraying chemicals while others aren't. It's that the atmosphere is heterogeneous and constantly changing. And yes, we should address the conspiracy theories directly. Some people believe contrails are actually chemtrails, deliberate chemical spraying for various nefarious purposes. Weather control, population control, mind control, depending on which theory you encounter. There is no evidence supporting these claims. What we see in the sky is exactly what the physics predicts. Water vapor from combustion, condensing and freezing in cold air. Atmospheric scientists, pilots, and aviation engineers all confirm this. The phenomenon has been understood and documented since World War II. If there were a global spraying program, it would require the cooperation of millions of pilots, engineers, fuelers, and maintenance workers across every airline in every country. The logistics of keeping such a program secret would be impossible, and someone would have found physical evidence by now. What you're seeing is ice, just ice, created by the same process that makes your breath visible on a cold morning, scaled up to jet engine proportions. There's genuine scientific interest in contrails beyond conspiracy theories. The climate effects are real and worth studying. Contrails do affect atmospheric radiation balance. Understanding when and where they form helps climate modelers account for aviation's full environmental impact. There's also interest in contrail prediction for aviation efficiency. If we can predict where contrails will form, aircraft could potentially adjust routes or altitudes to minimize their formation when the climate impact is unfavorable, while accepting them when they might have neutral or even beneficial effects. Research is ongoing. The science is genuine. It's just not about secret chemicals. So the next time you see aircraft crossing the sky, you can actually decode what you're seeing. A plane with no trail is flying through air that's warm or dry enough that no condensation occurs. A plane with a short dissipating trail is in cold but dry air. A plane with a long persistent trail is in cold, humid air where ice crystals can survive. If you see trails spreading into sheets, you're looking at conditions favorable for artificial cirrus formation. The aircraft are literally making clouds. Two planes at different altitudes will likely show different contrail behavior. Two planes at the same altitude might show different behavior if they're passing through different air masses. It's all thermodynamics, temperature, pressure, humidity, and the phase transitions of water. Physics you can see written across the sky in white lines of ice. The atmosphere is complex. Its properties vary in 3 dimensions and time. Aircraft passing through it sample these conditions and make them visible. Every contrail is a little weather report from 35,000 feet telling you about the temperature and humidity at cruise altitude. Speaking of weather phenomena affecting aircraft, ice formation on wings is a constant concern for pilots. The physics of why ice is so dangerous and how aircraft prevent it involves some fascinating engineering. I've covered that in another video.